Greetings. The topic of our lecture today is virtual work principles in the analysis of frames. This lecture is part of a series of lectures for the class CEE 235A Advanced Structural Analysis. Before I start on this particular topic, I'd like to give you a little perspective on why we are doing this, why we are trying to use the principle of virtual work to solve a problem that we are already able to solve using the techniques we have learned earlier. The short answer to that question is that the principle of virtual work allows us to extend the standard displacement-based method to the analysis of problems that involve complex loadings and geometry as well as inelastic material responses. And now here's the long answer. Recall that through our discussions in chapters 4 and 5, we learned how to construct a discrete system of equations which comprise a stiffness matrix times a vector of nodal displacements and rotations, and another vector on the right-hand side that represented the externally applied loads. Also recall that the stiffness matrix was constructed based on the knowledge of the exact solution to a linear elastic beam that is loaded at its two ends and/or along its lateral surface. Well, you already know that the analytical or exact solutions of the governing balance equations are not possible for inelastic beams, and this problem becomes very cumbersome even for linear elastic beams that are non-prismatic. Therefore, the standard displacement-based matrix method of analysis becomes useless under these kinds of circumstances because we will not be able to obtain the element stiffness matrix or the load vector in closed form. As we discussed in the preceding lecture, principle of virtual work enables us to construct approximate solutions when a beam's response or geometry gets complicated. Having said this, we're not going to devote a significant amount of time in this lecture to the determination of approximate solutions, although we'll see a few problems to that effect. Instead, we are going to see how the stiffness matrix and the force vector can be calculated using the principle of virtual work for linear elastic prismatic beams. Therefore, the general aim of our discussion today is to establish the algebra and the application of principle of virtual work to frame analysis. This discussion will hopefully allow you to make a smooth transition to the next course. That is the course on finite element analysis. That course is going to more or less pick up where I stop and take you deeper into approximate solution techniques for analyses of not only frames, but also of continuous media under applied mechanical and thermal loads. Now, here's an overview of the lecture today. First, we're going to talk a little bit about constructing a generic displacement field with unknown coefficients and learn some of the common terminology in this area. Then we're going to apply the principle of virtual displacements and use that principle to obtain the element stiffness matrix. We're going to apply these techniques to non-prismatic elements, and in this discussion you'll hopefully see how principle of virtual displacements can give you approximate solutions. And we'll finally conclude with the determination of equivalent nodal loads using the principle of virtual displacements. And as before, all of these sections are taken from your textbook, McGuire, Zymian, and Gallagher. So let us begin with our discussion on the nature of approximations, and in this particular case we'll be focusing on the shape functions. So now consider the displacement field given as follows, that it is interpolated using shape functions, which are all denoted by these ni, and they're functions of the coordinate system of our problem. If it's an axial problem, that will be x will be the axial coordinate, or if it's a three-dimensional problem, x would denote a vector with components x, y, z. Delta sub I denote the generalized coordinates. So, of course, this expression can be written more compactly as the sum from I equals 1 through to n being the total number of generalized displacements and their corresponding shape functions. And the same sum can be more compactly written as the inner product of two vectors, a vector of shape functions, n, and a vector of generalized coordinates, delta, shown as follows. So let us now specialize this discussion of shape functions to the axial problem. In an axial problem, we have a rod with two nodes, and its two ends will be tracked, and the left node will have a displacement degree of freedom u1, along the positive x direction, and a corresponding force, internal force F of x1. And the same is true for node 2 with subscript 2. If we intend to represent or approximate the axial displacement field with a linear function, this is what we would write. U of x would be equal to a constant a1 plus another constant a2 times x. So we could just view this approximation or representation as a linear combination of shape functions and generalized coordinates, in which case the first shape function would be 1, the first generalized coordinate would be a sub 1, and the second shape function would be x, and the second generalized coordinate would be a2. This would be fine, and we could proceed with this, but we could come up with a more intuitive representation of the same approximation or representation. We can do that, we can achieve that by converting these a's into nodal displacements. So instead of working with generic generalized coordinates, we'd like to work with generalized coordinates that represent physical quantities that we can immediately understand. And those would be, in this case, u1 and u2. Not only such a representation would give us an intuitive understanding of representations, but also it would facilitate an easier assembly of similar elements, which we could achieve by rendering their nodal displacements equal to each other where they are connected. So let's go on with the algebra. To do the conversion, I would evaluate u at 0, and from the right-hand side, the value would be a1, and that, of course, must be equal to u sub 1. And then if I evaluated u at L, the right-hand side would be now, with the substitution of u1 in place, u1 plus a2 times L, and from this we could compute what a2 is, which would be the difference in the two nodal displacements normalized by L. If we make these substitutions into the original expression for a1 and a2 that are now represented in terms of u1 and u2, I can rearrange that original expression into the following form, where now my shape function n1 would be 1 minus x over L, and my second shape function would be x over L, and now my generalized coordinates have physical meanings, which also, as I mentioned before, would facilitate easy assembly, u1 and u2. These shape functions are also known as interpolation functions for obvious reasons, and if I plotted them, you'll see they have a peculiar feature. n1 is 1 at where its nodal displacement is located, and is 0 at node 2, which is the other node in this problem. And n2 displays the same behavior, although it's just mirrored. We can easily extend the same discussion to the torsion problem, which is also a problem that can easily be approximated by a linear twist field, theta sub x. So that's the rotation about the x-axis. We know that the analytical solution for an end-loaded shaft would give us a linearly varying twist field. So this would, in that case, be an exact solution. And we can just rearrange this in the same way that we have done for the axial problem, and we would end up with identical shape functions, but of course different generalized coordinates. In this particular case, the generalized coordinates would be the end twisting angle values. Here's here's a different problem, which is the flexure problem. Let us assume that we're dealing with the flexure of a beam about the z-axis. So in this case, we would have theta sub z1 and theta sub z2 denoting the rotations about the z-axis at two ends of this beam, with m sub z1 and m sub z2 representing the corresponding moments. And we would have v sub 1 and v sub 2 denoting the transverse displacements at the left and the right nodes respectively, with f sub y1 and f sub y2 denoting the corresponding transverse shear forces. We know that for prismatic linear elastic beams that are loaded only at at their ends, the transverse displacement field would be a cubic polynomial. Here's a generic cubic polynomial, and you could view this as a linear combination of various shape functions with generalized coordinates a sub I. But again, these a sub I do not directly lend themselves to physical properties, so we should try to rearrange them and represent this transverse displacement field with generalized coordinates that are v1, v2, theta sub z1, and theta sub z2. To do that, first I will compute the corresponding rotation field by simply differentiating that cubic polynomial to obtain a quadratic polynomial a sub 2 plus 2a sub 3x, etc. And then I would evaluate those two functions at the ends. I would evaluate the transverse deflection field v at x equals 0. That would obviously equal to be equal to v sub 1. And from the right-hand side of the polynomial, we'll see that that is equal to simply a1. And we will do the same thing for v2, theta sub z1, and theta sub z2. So we have 4 equations there, which means that we should be able to use those 4 equations to determine the a sub I constants in terms of the nodal displacements v sub 1, v sub 2, and nodal rotations theta sub z1 and theta sub z2. So once we do that solution, we will obtain a sub 1 to be simply v1, a sub 2 to be theta sub z1, a sub 3 and a sub 4 are more complicated looking functions, but they are also now represented as all the as a function of nodal degrees of freedom. We can substitute these relations back into the original cubic polynomial and rearrange it by collecting all the terms that multiply v sub 1 together and calling that n1, and repeating the same procedure for all the other nodal degrees of freedom. And if you do the algebra, you'll find out that those shape functions n sub 1 through to n sub 4 are all cubic. They're all cubic functions, and we have a special name for them. We call them cubic Hermite or cubic Hermitian polynomials. And if I plotted them, they would look like this. So when you look at this plot along the axis of the beam, you should be able to immediately understand which one of these shape functions belong to which generalized coordinate. Each of these cubic functions are defined by 4 quantities, right? Because each cubic polynomial will require 4 coefficients. So the 4 quantities that define the shape of each of these 4 cubic polynomials that are plotted in here are their end values, so there are 2 of them, and their end rotation values. So let's take a closer look at n1. You see that the left value of n1 is 1, the right value is 0. The left and right rotations of n1 are both also zeros. And this is only expected because if I evaluated v at 0, I should get 1 times v1, and all the terms on the right-hand side should go to 0. All the other terms on the right-hand side should go to 0. And if I evaluated v prime at x equals 0, I should also get 0 from the contribution of this degree of freedom v1, right? So this is just a more useful representation of the transverse deflection field for a beam under flexural loads than the original basic standard cubic representation. So let us move on to a more complicated or sophisticated example, which is an example borrowed from your textbook from page 179. And our task here is to construct a set of polynomial shape functions for the axial member shown. Here we have 2 end nodes, which happen to be nodes 1 and 3, and the mid-side node, node 2. Since we have 3 nodes, we can afford a quadratic polynomial to approximate or represent the displacement field, and a generic quadratic polynomial looks like that. Now I'd like to rearrange this quadratic polynomial in terms of the nodal displacements of this problem, so the generalized coordinates are physically meaningful quantities. So if I evaluate the given displacement field at x equals 0 and set that result equal to u1, at x equals L and set that result equal to u2, and x equals 2L and set that result equal to u3, I will have obtained 3 relationships, three equations, which I can invert so that I can obtain the representations of A's in terms of the nodal displacements U's. And the algebra of that procedure yields the following. And if I substitute those A's into the original quadratic function, I will have obtained this representation. This is perfectly equivalent to the original one. It is still a quadratic approximation, but here these shape functions are paired up with nodal displacements, which happen to be the generalized coordinates of this particular representation. And if I plot them again, I should expect what they should look like. N1 should have a unit value at its own node, and it should have 0 values at the mid-side node as well as the right node, node 3. And you see that the blue N1 just does that. It has a value of 1 at node 1. It has a value of 0 at node 2, which is the middle of the rod. And it also has a value of 0 at node 3. And you see the same behavior from other shape functions. N2 is unit at the mid-side node, but has 0 values at the two end nodes, 1 and 3. Okay, so here's another example. Let us construct a set of shape functions for the transverse displacement that satisfies the governing ordinary differential equation exactly for a non-prismatic member. So this is a beam bending problem. We have 2 degrees of freedom per node, which are the transverse deflection and rotation degrees of freedom at nodes 1 and 2. And the cross section is described as follows. It's a rectangular cross section with a base length of b and a variable height. And the height varies according to the formula given on the left side. And when x is equal to 0, the height is equal to h1. When x is equal to L, the height becomes 2 times h1. So the cross-section varies. If the cross-section varies, then we should be really calculating the second moment of area for this cross-section because we're dealing with a flexural problem. So IZZ, the second moment of area about the z-axis, which is coming out from the plane of the slide or the board here, is simply given by bh cubed over 12. It's the simple basic formula. However, in this case, h is a function of x as opposed to being a constant across the length of the member. So IZZ is just simply this cubic formula given. Now we plug this back into the governing ODE with care. The governing ordinary differential equation is a fourth order ODE, but we need to make sure that we are differentiating the I correctly. So we'll substitute the I before we take the derivative, the outermost second 2 derivatives, right? And the result must be equal to 0 if the beam is just loaded at its ends and there are no transverse loads here, distributed loads. So this is our governing equation to solve. So we will try and solve that. We can again use the direct integration for the simple fourth order ODE. We will just pull out the constants of the problem and eliminate them from both sides of the equation. And that would give us the equation that you see in the middle, still a fourth order. So if we integrate that equation in the middle twice, we will get a linear function on the right-hand side. And on the left-hand side, we would get this cubic polynomial segment multiplying the second derivative of v. And then we would have to invert this and write the second derivative of v in terms of these integration constants c1 and c2, and carry out the integration 2 more times, producing an additional set of 2 integration constants. So we have now solved the governing ODE, and as before, we have obtained 4 integration constants, which should be determined from the boundary conditions. And when you look at this solution, this is an exact solution, but it is not a cubic polynomial. It includes a logarithmic term and fractional polynomials, 1 over 1 plus x over L, that kind of stuff. So if we wanted to approximate the solution to a problem like this with a cubic polynomial, cubic Hermite polynomials, that would not be an exact solution, as you now know. We can rearrange this new exact analytical solution for this non-prismatic beam and represent those integration constants as functions of nodal displacements and rotations. And the procedure is simple as before. We would just evaluate V and its first derivative at the two ends of the beam and setting those results equal to transverse deflections as well as rotations, and then invert those relationships to determine the C's in terms of the degrees of freedom. And then we would have obtained a proper shape function, which when plugged into the principle of virtual displacements would give us an exact solution for this rather unusual problem. Okay, so let's actually do that. Let's actually move on to the application of the principle of virtual displacements to the problem at hand so that we can obtain element stiffness equations, for example.